The cosmos appears as a swirling sea of chaotic fire and darkness. Carl Sagan once said the cosmos is within us. We are made of star stuff. This profound idea hints at a hidden truth beneath the universe's wild exterior. For centuries, from ancient sky watchers to today's physicists, we have searched for the underlying patterns in the chaos. You are about to discover 35 hidden patterns that reveal a secret order governing everything. This journey will show you how fractal geometry, orbital resonances, and the fabric of space-time are all connected by a deep, mathematical harmony. By the end, you will see the universe not as a random accident, but as a system with a hidden blueprint. What if the whirl of galaxies is just a mask for a deeper structure? How does the spin of a black hole connect to the arrangement of planets? What does the universe's hidden design say about our own place within it? Are you ready to look behind the veil of cosmic chaos? Look closely at the majestic spiral of the Whirlpool Galaxy. Its vast arms, a swirling vortex of billions of stars, trace a pattern that feels strangely familiar. This cosmic form mirrors a sequence of numbers discovered by an Italian mathematician centuries ago. A pattern that appears everywhere from the arrangement of leaves on a stem to the spiral of a seashell. This is the Fibonacci sequence. Each number in this sequence is simply the sum of the two before it, starting with 0 and 1. So it goes 0, 1, 1, 2, 3, 5, 8, 13, and so on, continuing infinitely. When you plot these numbers geometrically, they create a graceful, ever-widening spiral. Astronomers have found that the arms of many spiral galaxies, including our own Milky Way, often follow this same logarithmic spiral, a curve whose growth is governed by the Fibonacci numbers. This is not a perfect one-to-one match, but the underlying mathematical principle is strikingly similar. As one astrophysicist noted, it suggests that the same universal rules of mathematics that dictate efficient growth in a sunflower's seed head might also be sculpting entire galaxies. The Fibonacci spiral represents a way for a structure to expand without changing its shape, packing the most material into the smallest space as it grows. This principle of optimal packing and expansion seems to be a universal constant. You can see it in the tight coil of a nautilus shell, designed for efficient growth, and you can see it in the furious swirl of a hurricane, a pattern shaped by the same fluid dynamics that might operate on a galactic scale. So when we gaze at a spiral galaxy, we are not just looking at a random collection of stars. We are witnessing a fundamental pattern of growth, written into the fabric of the cosmos itself. Does this mathematical recurrence, from the smallest shell to the largest galaxy, hint at a universal blueprint for how things form and evolve? This pattern of growth in space leads our eyes to the patterns of motion, the rhythmic dances that govern celestial bodies. Far from the serene spiral of galaxies, a frantic dance unfolds in the orbit of Jupiter. Three of its largest moons, Io, Europa, and Ganymede, are locked in an intricate gravitational waltz. For every single orbit Ganymede completes around Jupiter, Europa completes exactly 2, and fiery Io completes precisely 4. This perfect celestial rhythm is not a coincidence. It is a powerful demonstration of orbital resonance, a phenomenon where the gravitational tug between orbiting bodies synchronizes their paths in stable, repeating patterns. This is the music of the spheres, a literal harmony written in the language of gravity and motion. As one planetary scientist beautifully described it, these resonances act like a cosmic metronome, keeping time for the entire system and preventing the chaotic collisions that would otherwise tear it apart. The key to this stability lies in the simple integer ratios governing their orbits, like the 1:2:4 ratio of Jupiter's moons. When one body completes one orbit, another completes 2, and their gravitational nudges consistently reinforce each other in the same places, creating a balanced and predictable cycle. This hidden order is not confined to Jupiter. In the distant reaches of our own solar system, Neptune and Pluto are locked in a resonance. For every 2 orbits Neptune makes around the Sun, Pluto makes 3. This gravitational handshake ensures they never get too close, maintaining a peaceful coexistence across billions of years. We see this same principle at work in other star systems. The 7 Earth-sized worlds of the TRAPPIST-1 system are all bound together in a complex chain of resonances, their orbits ticking in sync like a perfectly engineered clock. And we can even see the effects of resonance sculpting the cosmos on a smaller scale. The dark gaps within Saturn's magnificent rings are not empty. They are the direct result of orbital resonances with the planet's moons. The consistent gravitational pull from a moon like Mimas clears out any ring particles that would otherwise orbit at that specific distance, carving out a visible line of order from the apparent chaos. So many worlds are held in these silent, rhythmic embraces. What other symphonies, composed by gravity and conducted by mathematics, are playing out in the darkness? This grand harmony of orbits points toward an even larger structural design woven into the fabric of the universe itself. Stretching across unimaginable distances, an invisible architecture holds the universe together. Picture a spiderweb on a dewy morning, its delicate strands glistening, each line perfectly placed to create a resilient whole. Now, magnify that image to a cosmic scale. This is the cosmic web, the largest pattern in existence, and its threads are woven not from silk, but from the most mysterious substance we know, dark matter. We cannot see it, touch it, or directly observe it, because dark matter does not interact with light. Yet its immense gravitational pull is the master architect of the cosmos, sculpting the distribution of all the galaxies we can see. Through sophisticated computer simulations that model the evolution of the universe, a stunning picture emerges. Galaxies are not scattered randomly through the void. Instead, they cluster along immense, tangled filaments of dark matter, like glittering dewdrops caught on a vast, invisible web. These filaments stretch for billions of light years, connecting at dense nodes where immense clusters of thousands of galaxies reside, while leaving behind enormous, empty voids of near-nothingness. A leading cosmologist once described this web as the fundamental scaffold of the universe, the framework upon which the visible world is built. But how did this intricate pattern begin? Its origins lie in the first fleeting moments after the Big Bang. The infant universe was not perfectly smooth. It contained incredibly tiny fluctuations, minute differences in density from one patch of space to another. Over billions of years, gravity relentlessly worked on these tiny seeds. Regions with slightly more density pulled in more dark matter, growing denser and denser, while less dense regions were left behind. This gravitational amplification sculpted the primordial soup into the vast, web-like structure we see today. So how do we map something we cannot see? Astronomers use the subtle effects of gravity on light itself, a phenomenon called gravitational lensing. The immense mass of a dark matter filament bends the path of light from galaxies far behind it, distorting their images like a funhouse mirror. By carefully studying these distortions, we can trace the outline of the invisible web. Another method involves massive galaxy surveys, like the monumental Sloan Digital Sky Survey. This project meticulously mapped the positions of millions of galaxies, creating a three-dimensional atlas of the cosmos. When you plot all those points, the web pattern emerges with breathtaking clarity, a cosmic fingerprint revealing the hidden hand of dark matter. If dark matter is the frame, what does that tell us about the painting of the universe? It suggests that everything we see, every star and every galaxy, is merely the visible decoration on a much deeper, hidden structure. This grand design, written in gravity, finds an echo in the universe's oldest surviving light. Frozen in the depths of space is the oldest photograph ever taken, a snapshot of the infant universe. This is the cosmic microwave background, the faint afterglow of the Big Bang itself, cooling and stretching over nearly 14 billion years into a microwave whisper that permeates all of space. To our most sensitive instruments, this background appears almost perfectly uniform, a smooth sea of radiation. But hidden within this uniformity are the most crucial patterns of all, tiny anisotropies, which are minute variations in temperature, mere millionths of a degree warmer or colder than their surroundings. These faint hot and cold spots are not random noise. They are a cosmic blueprint, the encoded seeds from which every star, every galaxy, and the vast cosmic web itself would eventually grow. As one Nobel laureate in physics profoundly stated, studying these fluctuations is like reading the genetic code of the universe. Missions like the Planck satellite have spent years meticulously mapping this ancient light, creating a full sky picture of these subtle imperfections. So what do these hot and cold spots actually represent? Each one is a fossil imprint of the universe's earliest moments. A slightly warmer region corresponds to a patch of space that was a little denser, packed with a little more matter and energy. A slightly cooler spot marks a region that was a little emptier, a slight void. In the dense soup of the early universe, gravity began its slow, relentless work on these tiny seeds. The slightly denser, hotter regions had stronger gravity, pulling in even more material from their surroundings. Over hundreds of millions of years, these regions grew denser and denser, eventually collapsing under their own weight to form the first clumps of matter, the first stars, and the first galaxies. The emptier, cooler regions, meanwhile, were left behind, evolving into the great cosmic voids we see today. The entire grand structure of the modern cosmos, from the smallest dwarf galaxy to the largest supercluster, was predetermined by the pattern of these anisotropies. The precise nature of these patterns, their size and distribution, has revealed the universe's deepest secrets to scientists. They tell us the exact age of the cosmos, its overall geometry, and its surprising composition, dominated by dark matter and dark energy. So what other secrets about our cosmic origins are frozen in this ancient light? These primordial patterns, the very cause of cosmic structure, are intimately connected to a mysterious force that now tears the universe apart. The universe is not merely expanding, it is running away from itself. This startling discovery, which earned the Nobel Prize in Physics, overturned a fundamental assumption held for decades. Astronomers had long believed that the mutual gravitational pull of all the matter in the cosmos would eventually slow its expansion, perhaps even reverse it in a great collapse. Instead, they found the opposite is true. The expansion of space is accelerating, and a mysterious force, which we call dark energy, is the engine driving this runaway process. This force is now the dominant component of our universe, making up about 70% of its total energy budget. Yet we have no idea what it actually is. The pattern revealing this profound shift is etched into the light of dying stars. When astronomers observe extremely distant galaxies, they are looking back in time. By measuring how fast these galaxies are receding from us, a clear and unsettling order emerges. The farther away a galaxy is, and thus the further back in time we see it, the slower it appears to be moving away. The closer, more recent galaxies are fleeing faster. This pattern of increasing velocity over cosmic time can mean only one thing: the expansion of the universe is speeding up. As one theoretical physicist has pondered, the simplest and most profound explanation is that dark energy is an intrinsic property of empty space itself. The vacuum of space, according to this idea, is not truly empty. It possesses a fundamental energy that causes space itself to stretch, and as more space comes into existence, more of this repulsive energy appears, creating a self-perpetuating cycle of acceleration. The key evidence for this cosmic acceleration came from observing a specific kind of stellar explosion, a type Ia supernova. These supernovae occur when a white dwarf star steals enough material from a companion to trigger a cataclysmic detonation. Because the explosion always happens at almost exactly the same mass, these events have a known, predictable brightness. They are perfect standard candles. By comparing how bright these supernovae appear from Earth to how bright we know they actually are, astronomers can calculate their precise distance. Then, by analyzing the redshift of their light, they can determine how fast they are moving. The data from the Hubble Space Telescope and from massive, ground-based sky surveys consistently showed that these distant standard candles were significantly fainter, and thus farther away, than they should have been if the universe's expansion were constant or slowing. The only explanation was that the expansion had been slower in the past, and has been accelerating for billions of years. This relentless acceleration paints a stark picture of the universe's ultimate fate. If dark energy continues to dominate, the expansion will continue to accelerate indefinitely. Galaxies outside our local group will be pushed away so fast that their light will no longer be able to reach us. The observable universe will shrink to a small, lonely collection of stars, surrounded by an ever-deepening and impenetrable darkness. This scenario is often called the Big Freeze, a cosmos where space becomes so vast and empty that all activity and heat eventually fade away. So we are left with a deep and haunting question. Is dark energy the ultimate manifestation of a hidden cosmic order, a fundamental constant of nature as regular as the patterns of a snowflake? Or is its repulsive force the signature of a deeper, underlying chaos, a wild card that forever reshapes the destiny of everything? This immense force dictating the fate of the cosmos finds a strange and tiny mirror in the quantum realm, where another kind of hidden order governs the behavior of the very small. The vacuum of space is not a silent emptiness, but a seething, bubbling sea of energy. This restless activity is governed by the sixth hidden pattern, the dance of quantum fluctuations and virtual particles. According to our most fundamental theories of physics, empty space is not truly empty. At the tiniest imaginable scales, a constant, churning process unfolds. For fleeting moments, pairs of particles and their antimatter counterparts spontaneously pop into existence, borrowing energy from the vacuum before almost instantly annihilating each other and vanishing. These are virtual particles, and their brief, frantic lives are a direct result of temporary changes in energy known as quantum fluctuations. This ceaseless creation and destruction is not chaos. It is a fundamental, rhythmic pattern of quantum field theory, a hidden order underlying what appears to us as perfect stillness. As one quantum physicist eloquently put it, the vacuum is alive with a vibrant potential. We can even observe the effects of this activity in laboratory experiments. The Casimir effect provides a stunning demonstration. When two uncharged metal plates are placed incredibly close together in a vacuum, they are gently pushed toward each other. Why? Because the space between the plates is so narrow that only virtual particles with certain wavelengths can flicker into existence there. The space outside the plates, however, allows for a much wider variety of particles. This difference in quantum activity outside and inside creates a subtle pressure that forces the plates together, a measurable force born from apparent nothingness. These fluctuations also leave their mark on the very building blocks of matter. The Lamb shift is a tiny but crucial change in the energy levels of the hydrogen atom, a shift that classical physics could not explain. It was only through understanding the interaction between the atom's electron and the virtual particles of the quantum vacuum that physicists could account for this precise measurement. The influence of these tiny ripples extends far beyond the laboratory, all the way to the birth of the cosmos. The theory of cosmic inflation suggests that the entire vast universe we see today underwent a period of unimaginably rapid expansion in its first fraction of a second. What could have possibly triggered such an event? Many cosmologists point to a single colossal quantum fluctuation, a tiny patch of space, energized by a random fluctuation, may have crossed a critical threshold, tipping the universe into that explosive inflationary phase that set the stage for everything to come. Perhaps the most profound consequence of this quantum dance is Hawking radiation. At the very edge of a black hole, right at the precipice of the event horizon, virtual particle pairs are constantly emerging. Usually, they annihilate each other instantly. But if one particle of the pair falls across the event horizon while its partner escapes, the black hole loses a tiny amount of mass in the process. Over eons, this slow trickle of escaping particles causes the black hole to evaporate. Here, the smallest quantum process dictates the ultimate fate of the most gravitationally powerful objects in the universe. This leads to a staggering possibility. Could our entire cosmos, with all its galaxies and stars, be the final macroscopic consequence of a single, primordial quantum fluctuation? These tiny, spontaneous ripples in the fabric of reality appear to be the seeds from which the largest structures grow, proving that the patterns of the very small are inextricably woven into the fate of the very large. Ancient light carries a whisper of the universe's first shudder. When we think of light, we often picture a simple wave, but it can also wiggle in a specific direction, a property known as polarization. You experience this every time you put on a pair of polarized sunglasses, which cut down on glare by blocking light waves oscillating horizontally. The faint afterglow of the Big Bang, the cosmic microwave background, is also polarized. This subtle pattern is not just a curiosity. It is a direct message from the universe's most violent and formative instant, a period of hyper-expansion called inflation that occurred in the first trillionth of a second. A leading cosmologist working on the BICEP array at the South Pole has described the hunt for this specific polarization as the search for the holy grail of cosmology, a way to see directly back to the beginning of time itself. The polarization in the CMB comes in two distinct types, each telling a different part of the story. The first, called E-mode polarization, is the simpler of the two. It is primarily a result of the density fluctuations in the early universe, the same hot and cold spots we discussed before. As these slight overdensities and underdensities evolved, they created moving waves of plasma, and the light scattering off this moving material became polarized in a curling, radial pattern, like the petals of a flower. This pattern was detected over a decade ago and beautifully confirmed our models of the universe's structure. But the second type, B-mode polarization, is the true prize. This pattern has a twisting, curl-like quality, and it is believed to be the unique signature of primordial gravitational waves. These are not waves in water or air, but literal ripples in the fabric of spacetime itself, generated by the ferocious energy of the inflationary expansion. Detecting these B-modes would be like finding the fossilized imprint of the Big Bang's first tremors. The technological challenge in this search is immense. The signal is incredibly faint, a whisper buried under a cacophony of foreground noise. The biggest contaminant is dust right here in our own galaxy. Tiny, elongated grains of interstellar dust, when aligned by magnetic fields, can also emit polarized light that mimics the very B-mode signal scientists are desperately seeking. This challenge was brought into sharp focus with the BICEP-2 experiment's announcement. The team believed they had found the first direct evidence of primordial gravitational waves, a discovery that would have guaranteed a Nobel Prize. The celebration was short-lived. Further analysis, crucially incorporating data from the Planck satellite, revealed that the signal they detected was almost entirely due to this confounding galactic dust. It was a sobering lesson in cosmic humility, and the painstaking rigor required to separate the true signal of creation from local interference. So what can the subtle twisting of this ancient light truly tell us about the first trillionth of a second of time, It would reveal the energy scale at which inflation happened, telling us what kind of physics governed the universe at energies a trillion times greater than what our most powerful particle colliders can achieve. This search for a primordial signal in the sky is perfectly mirrored in the patterns of matter we see around us today. Long after the primordial gravitational waves faded, a different kind of wave was crashing through the infant cosmos. The early universe was a seething ocean of plasma, a hot, dense soup of particles and light, where pressure waves raced outward at over half the speed of sound. These were not silent ripples, but the universe's first and loudest sound, a deep bass note thrumming through creation. When the universe cooled enough for atoms to form, about 400,000 years after the Big Bang, this chaotic symphony suddenly stopped. The waves froze in place, their final positions etched permanently into the cosmos. This fossilized imprint is the eighth hidden pattern, known as Baryon acoustic oscillations. It is a cosmic yardstick, a standard ruler of known length that astronomers use to measure the geometry and expansion of the universe with incredible precision. A lead researcher from the Sloan Digital Sky Survey once described this pattern as a gift from the early universe, a built-in measuring tape that allows us to survey the largest structures with confidence. The origin of this pattern lies in a fierce tug-of-war that played out in the primordial plasma. Imagine a dense knot of matter, a region packed with protons, neutrons, and electrons, all bathed in intense light. Gravity relentlessly tried to pull this knot inward, collapsing it, but the immense pressure of the trapped radiation fiercely pushed back, creating a powerful pressure wave that expanded outward like a spherical sonic boom. This wave traveled for hundreds of thousands of years, carrying a shell of ordinary matter, which we call baryons. Then, in an instant, cosmically speaking, everything changed. When the universe cooled and atoms formed, the light that had been trapped suddenly streamed freely across space. The pressure support vanished, and the wave simply stopped in its tracks, leaving behind a spherical shell of matter with a very specific radius. This process happened everywhere at once, creating a universe with a subtle preference for pairs of galaxies to be separated by this exact distance, about 500 million light-years. How do we possibly see this pattern today? Through massive galaxy surveys that map the three-dimensional positions of millions of galaxies. When astronomers analyze this cosmic cartography, they do not see perfect spherical shells. Instead, they find that if you take any galaxy, you are statistically more likely to find another galaxy at that specific, characteristic distance from it than at any other separation. It is a subtle statistical peak in the data, a ghostly echo of that primordial sound wave. This cosmic ruler is incredibly powerful because its true length is known from our understanding of the early universe. By observing how this apparent length changes at different distances, and thus at different look-back times, astronomers can measure how the expansion rate of the universe has changed over billions of years. This data provides one of the most stringent independent tests for the existence and nature of dark energy, confirming that the expansion is indeed accelerating. It also tightly constrains the geometry of the cosmos, confirming it is flat to within a remarkable margin of error. So how does the echo of the universe's first sound guide our understanding of its fate? It gives us a fixed point of reference in an ever-expanding cosmos, a way to measure the stretch of spacetime itself. These acoustic patterns are part of a larger statistical description of the cosmos, a hidden rhythm that connects the universe's fiery birth to its accelerating present. This near-perfect initial state of the universe is described by a profound mathematical pattern known as the Harrison-Zeldovich Spectrum. It reveals that the cosmos did not begin with random clumpiness, but with a very specific and elegant distribution of its primordial seeds. This spectrum is the precise blueprint for the density fluctuations that would later grow into galaxies and clusters, and its most stunning property is that it is nearly scale invariant. A Nobel Prize-winning cosmologist has called the discovery of this pattern a holy grail for modern cosmology, a triumphant confirmation of the inflationary theory. But what does scale invariance truly mean in this cosmic context? It means the initial level of lumpiness was almost exactly the same, regardless of the size of the region you examine. Whether you zoom into a patch of space destined to become a single galaxy or zoom out to a region that would evolve into a massive supercluster spanning hundreds of millions of light years, the relative amplitude of the density variations was remarkably similar. This is not a pattern you would expect from a chaotic beginning. It is the signature of a highly ordered and finely tuned process. You can see an echo of this principle in certain fractal patterns in nature, like a Romanesco broccoli, where the swirling, conical shapes look roughly the same whether you look at the entire vegetable or just a single, tiny floret. The universe's initial conditions possessed a similar kind of self-similarity. The evidence for this scale-invariant spectrum is written clearly across the sky. It is imprinted in the statistical properties of the cosmic microwave backgrounds, hot and cold spots, which show fluctuations of the same relative strength whether they are large or small. This same initial pattern then propagated forward through time, governing the distribution of galaxies we map in the cosmic web today. The large-scale structure we see, with its vast filaments and great voids, is the direct grown-up consequence of this infant-scale uniformity. So does this universal initial condition point toward a fundamental simplicity underlying all the complexity we observe. The Harrison-Zeldovich spectrum suggests that for all its grand diversity, the universe was born from a state of profound and elegant harmony, a single mathematical rule that set the stage for everything to come. Gazing into the Hubble Deep Field is like looking through a keyhole into a cosmic metropolis, a single patch of sky revealing thousands of galaxies, each a swirling island of stars. This breathtaking variety is not a chaotic free-for-all. Underlying this cosmic skyline is a deep and predictable rhythm, the 10th hidden pattern, known as the galaxy mass function. This pattern describes a simple but profound rule, a census of the stellar universe. There are an immense number of very small, dwarf galaxies, a moderate number of mid-sized galaxies like our Milky Way, and only a handful of truly colossal giants. This distribution is not random. It follows a precise mathematical curve that reveals the entire history of how galaxies are built. As one astrophysicist put it, the mass function is a fossil record of hierarchical structure formation, telling the story of how small pieces assembled into the grand structures we see today. This story begins with the scaffolding of dark matter. After the Big Bang, tiny dark matter halos began to form, and over billions of years, these halos constantly merged, with smaller ones being swallowed by larger ones. As a dark matter halo grew, its gravity pulled in vast clouds of hydrogen gas. This gas settled into the halo's center, cooling and fragmenting until it ignited into the first brilliant fires of stars, birthing a galaxy. The pattern we see today, with many small galaxies and few large ones, is a direct result of this assembly process. More small halos form initially, and while many merge to build larger galaxies, countless others survive as the dwarf galaxies we observe orbiting larger hosts like our own. But gravity alone does not tell the whole story. The final shape of the mass distribution is sculpted by fierce and dynamic processes within the galaxies themselves. When massive stars explode as supernova, they unleash tremendous blasts of energy that can heat surrounding gas or even blow it entirely out of the galaxy, shutting down future star formation. In the most massive galaxies, the supermassive black holes at their centers can become active galactic nuclei, pouring out intense radiation that also regulates gas accretion and star birth. This balancing act, between the inward pull of gravity and the outward push of feedback, is what carves the characteristic shape of the mass function. This shape is perfectly described by a mathematical formula known as the Schechter function. It is an elegant curve that captures the overwhelming abundance of low-mass galaxies, the steady decline of heavier ones, and a sharp cutoff at the very high mass end, a point beyond which we find almost no galaxies. This mathematical form fits the observed data with remarkable precision, confirming that a universal set of rules governs galaxy growth. Our own Milky Way is a perfect example of a galaxy on the more massive side of this distribution, a large spiral, but it is far from the largest. It is surrounded by a swarm of dozens of known dwarf galaxies, tiny satellites that represent the far more common, small building blocks of the cosmic landscape. What does the overwhelming commonality of these small, faint galaxies tell us about the fundamental building blocks of the cosmos? It suggests that the universe prefers to construct its grandest designs from humble beginnings, assembling giants one tiny piece at a time. This distribution of galactic mass is inextricably linked to the lives and deaths of the stars that fill them, a cycle of creation and destruction written into the very fabric of each island universe. Deep within the cosmic nurseries of vast, cold molecular clouds, a silent and prolific factory is at work. This is the origin point for the 11th hidden pattern, the initial mass function of stars. When a cloud of gas collapses under its own gravity, it does not form a single, uniform type of star. Instead, it shatters into a whole spectrum of stellar masses, from the tiniest smoldering embers to brilliant, short-lived behemoths. The initial mass function is the statistical rulebook for this process. It describes the predictable distribution of stellar masses at the moment of their birth, and its most astounding feature is its universality. From our own Milky Way to galaxies billions of light years away, this fundamental distribution appears to be the same, suggesting that a common, underlying physics governs star formation across the cosmos. A prominent stellar astronomer has noted that the IMF is the single most important factor determining a galaxy's destiny, as it dictates the total amount of light, the flood of ultraviolet radiation, and the rate at which heavy elements are forged and scattered into space. The typical IMF reveals a universe that strongly favors the small and humble. For every single star like our Sun, there are hundreds of smaller, cooler red dwarf stars. These dim, long-lived stars are the silent majority of the cosmos, vastly outnumbering all other types combined. The brilliant O and B-type stars, those dazzling blue giants that dominate a galaxy's light, are incredibly rare. Why does nature follow this particular pattern? The answer lies in the chaotic physics of the stellar nurseries themselves. As a giant molecular cloud collapses, it is not a smooth process. It is filled with supersonic turbulence, a churning mess of shockwaves and competing gravitational pulls. This turbulence causes the cloud to fragment into clumps of different sizes. Most of these clumps are small, destined to become red dwarfs. Only a few regions manage to accumulate and hold onto enough gas to create a true stellar giant. This is a cosmic game of chance, weighted heavily toward producing small winners. You can see this distribution beautifully illustrated in a young, nearby star cluster like the Pleiades. To the naked eye, a handful of brilliant blue stars dominate the scene, but through a telescope, a swarm of fainter, smaller stars is revealed, the countless more common siblings that make up the bulk of the cluster's population. So why does the universe prefer to make small, dim stars over brilliant giants? This fundamental birth function does not just populate galaxies, it directly sets the stage for their most spectacular and transformative events, the violent deaths of stars. A brilliant insight into the cosmos began not with a telescope, but with a human eye meticulously studying photographic plates. In the early 1900s at the Harvard College Observatory, a remarkable astronomer named Henrietta Leavitt was cataloging stars in the small Magellanic Cloud. She focused on a particular class of stars called Cepheid variables, which rhythmically brighten and dim over days or weeks. Leavitt noticed something extraordinary. The longer a Cepheid's pulsation period, the brighter its intrinsic luminosity appeared to be. She had discovered a direct relationship between the star's internal clock and its true power output, a pattern that would become one of the most important tools in astronomy. A historian of science later described this discovery as the yardstick for the heavens, a simple key that unlocked the vast scale of the universe. This period-luminosity relationship meant that by simply measuring how long it took a Cepheid to pulse, astronomers could determine its true brightness. By comparing that known true brightness to how dim it appeared from Earth, they could calculate its distance with unprecedented accuracy. For the first time, humanity had a reliable standard candle to measure distances far beyond our own galaxy. But what physics causes a star to beat with such reliable regularity? The mechanism lies in a delicate dance of ionization deep within the star's outer layers. A Cepheid is not a perfectly stable ball of gas. In its helium-rich outer envelope, the intense heat can strip electrons from atoms, a process known as ionization. When the star is at its dimmest, this ionized helium is very opaque, trapping radiation and causing the outer layers to heat up and expand. As the star expands, however, the pressure drops, allowing the helium to recombine with electrons and become transparent again. This newfound transparency allows the pent-up radiation to escape, and without that internal pressure, gravity pulls the outer layers crashing back inward. The compression reheats the helium, re-ionizing it and making it opaque once more, trapping radiation and starting the entire cycle again. This self-regulating pulsation, a cycle of ionization and recombination, creates a perfect cosmic metronome. The period of this beat is directly tied to the star's average density, which in turn dictates its intrinsic luminosity, forging the unbreakable link that Leavitt uncovered. This powerful tool allowed Edwin Hubble to make his paradigm-shattering discovery. By identifying Cepheid variables in the Great Spiral Nebula of Andromeda, he was able to calculate its distance. The result was staggering. Andromeda was millions of light-years away, a separate island universe far beyond the confines of our Milky Way. This single measurement instantly expanded the known universe and paved the way for his later discovery of the expanding cosmos. How did the rhythmic beating of distant stars unveil the scale of the universe? It provided the first crucial rung on the cosmic distance ladder, a stepping stone that transformed faint smudges of light into recognizable galaxies, revealing a cosmos vaster than anyone had dreamed. This stellar metronome is one of many cosmic clocks, a precise rhythm that guides us through the expanding darkness. A spiral galaxy rotates not as a rigid pinwheel, but as a fluid, its outer stars whipping around at a velocity that defies simple expectation. This motion holds the key to the 13th pattern, the Tully-Fisher relation, a profound link between a galaxy's spin and its shine. By observing the faint radio emission from neutral hydrogen gas, the famous 21-centimeter line, astronomers can measure how fast a spiral galaxy is rotating. They discovered a startlingly tight correlation. The faster a spiral galaxy spins, the more luminous it is. This is not just a curiosity, it is a cosmic speedometer that doubles as a distance finder. An extragalactic astronomer might explain that this relation emerges from the most fundamental property of all, mass. A galaxy's rotation speed is dictated by the total gravitational pull holding it together, a pull dominated by its invisible dark matter halo. The more massive the dark matter halo, the faster the stars and gas within it must orbit to avoid being flung out into the void. This is where the connection to light becomes clear. A more massive halo can pull in and retain more gas, which in turn forms more stars. So a faster spin indicates a heavier dark matter halo, which leads to a greater reservoir of gas, resulting in a brighter galaxy. The evidence for this dark matter link is written in the galaxy's rotation curve, a graph of orbital speed versus distance from the center. If galaxies were made only of visible stars and gas, we would expect stars in the outer disk to slow down, just as Pluto orbits the Sun more slowly than Mercury. But they do not. The rotation curve remains flat far out into the invisible reaches of the galactic disk, a sure sign that an immense sphere of unseen matter envelops the visible galaxy, its gravity governing the motion from the shadows. This makes the Tully-Fisher relation a powerful independent tool for cosmic cartography. By simply measuring a distant spiral's rotation speed from its hydrogen signature, astronomers can immediately deduce its true luminosity. Comparing that intrinsic brightness to its apparent dimness from Earth gives a direct measurement of its distance. In massive surveys mapping the large-scale flow of galaxies, this relation is indispensable. Imagine a fast-spinning spiral, its arms a blur of stellar motion, shining with the fierce light of billions of stars. Now picture a slower, more sedate spiral, its rotation more leisurely and its glow far more modest. The Tully-Fisher relation tells us that the difference in their brilliance is not random. It is a direct consequence of the depth of the gravitational wells they sit in, wells carved by dark matter. What does the universal nature of this relation say about the consistency of galaxy formation? It suggests that the intricate dance between dark matter and luminous matter follows a single, predictable set of rules, a universal recipe for building a spiral galaxy. This elegant dynamic for spiral galaxies finds its counterpart in the very different, but no less ordered, world of featureless ellipticals. While spiral galaxies rotate with a clear, flat plane of motion, elliptical galaxies present a very different kind of order. They are vast, smooth swarms of ancient stars, lacking the distinctive arms and gas disks of their spiral cousins. Their stars do not orbit in an orderly disk but buzz in every direction, like a furious swarm of bees. Yet, within this apparent chaos, a deeper pattern emerges, a hidden correlation known as the fundamental plane. This is a three-dimensional relationship connecting an elliptical galaxy's size, its surface brightness, and the random velocity of its stars. These three observable properties are locked together in a tight conspiracy. A pattern so precise it reveals the fundamental physics governing these stellar cities. A galaxy dynamicist might describe the fundamental plane as the direct consequence of the virial theorem, a cornerstone of physics that balances the kinetic energy of a system's random motions against its gravitational potential energy. In essence, the stars in an elliptical galaxy are in a state of equilibrium, held together by gravity and kept from collapsing by their own frantic, random speeds. The fundamental plane is the mathematical expression of this balance. If you know two of the properties, such as the galaxy's size and the spread of its stars' velocities, the third property, its brightness, is almost perfectly determined. Deviations from this plane are rare and incredibly telling. A galaxy that sits slightly off the fundamental plane may have experienced a recent merger, a violent event that injected new energy and disturbed the delicate equilibrium. It could also indicate a unique history of star formation, where the galaxy used up its gas supply in a sudden burst, leaving behind a stellar population that doesn't quite match the standard model. This makes the plane a powerful diagnostic tool for studying galaxy evolution across cosmic time. Astronomers also use this relation as a robust distance indicator. By measuring a galaxy's apparent size and the velocity dispersion of its stars from Earth, they can pinpoint its position on the fundamental plane and thus deduce its true intrinsic brightness. Comparing this true brightness to its observed dimness gives a direct measure of its distance, a method crucial for probing the large-scale structure of the distant universe. Consider the giant elliptical galaxy M87, the dominant galaxy at the heart of the Virgo cluster. Its image is iconic, a featureless golden glow from which a colossal jet of plasma erupts. When astronomers plot M87's properties, they find it sits perfectly on the fundamental plane. Its immense size, its relatively dim surface brightness spread across that vast area, and the high-velocity dispersion of its stars are in perfect harmony, a testament to a long, stable life governed by the simple laws of gravitational physics. Does this three-dimensional relationship hint at a universal recipe for making elliptical galaxies? It suggests that despite their varied appearances and histories, these galaxies are all shaped by the same fundamental forces, converging onto a single plane of existence defined by gravity and motion. The scaling relations of galaxies extend to the most massive structures in the universe. A city of 1,000 galaxies drifts through the cosmic void, its streets traced by the collective glow of countless stars. This is a massive galaxy cluster, and hidden within its apparent sprawl is the 15th pattern, the cluster mass-richness relation. The rule is elegantly simple. The more galaxies a cluster contains, a property astronomers call its richness, the more massive it is. This correlation is so reliable that scientists can estimate the total weight of these colossal structures, which is dominated by dark matter, simply by counting the visible galaxies within them. A cluster cosmologist might explain that we calibrate this cosmic scale using two powerful techniques. The first is gravitational lensing, where the cluster's immense gravity bends the light from background galaxies, allowing us to directly map its total mass. The second involves observing the seething cloud of hot gas trapped within the cluster's gravitational grip. By measuring the temperature and distribution of this gas with X-ray telescopes, we can weigh the entire system, confirming the deep link between a high galaxy count and a truly immense dark matter halo. This pattern emerges from the very origins of cosmic structure. Clusters do not form randomly. They are the end products of hierarchical growth, assembling over billions of years in the densest peaks of the primordial matter distribution. A region of space that started with a slightly larger density fluctuation would pull in more dark matter, which in turn attracted more galaxies through mergers and accretion, naturally leading to a richer, more massive final cluster. This makes the mass-richness relation a vital tool for modern cosmology. In vast surveys like the Dark Energy Survey, astronomers systematically scan the sky, identifying clusters and counting their member galaxies. By tracking how the number of clusters of a given richness changes across different cosmic epochs, they can measure the influence of dark energy on the growth of these largest structures, tightening the constraints on the universe's accelerating expansion. Consider the Coma cluster, one of the richest and most massive clusters known in our cosmic neighborhood. It is a sprawling metropolis of over 1,000 identified galaxies, all bound by a gravitational pull so powerful that it governs the motion of its members across millions of light years. What does this predictable link between a simple galaxy count and total mass reveal about the fairness of cosmic structure formation? It suggests that the universe builds its grandest assemblies by a consistent and measurable set of rules, where the visible abundance of galaxies is a direct reflection of the invisible depth of the gravitational well they share. The properties of these immense clusters are also revealed by the hot gas within them. The oldest light in the universe carries a ghostly imprint of everything it has passed through. After traveling for nearly 14 billion years, a photon from the cosmic microwave background can have its final journey interrupted as it plunges through a massive galaxy cluster. There, it encounters a seething ocean of superheated gas, a plasma so fierce that electrons swim freely at temperatures of millions of degrees. This encounter triggers the 16th hidden pattern, the Sunyaev-Zeldovich Effect. As one observational cosmologist noted, this phenomenon allows us to see the shadow of a galaxy cluster's immense pressure against the backdrop of the primordial fire, a way to find these cosmic giants no matter how far away they are. The physics at play is a process called inverse Compton scattering. When a low-energy CMB photon collides with a high-energy electron in the intracluster gas, the electron transfers a tiny amount of its own energy to the photon. It is like a slow-moving marble being struck by a much faster one. The slow marble gets a significant kick. For the CMB, this means that its photons are boosted to slightly higher energies. This creates a specific, telltale distortion in the CMB map. At the frequencies where the CMB is normally brightest, the cluster casts a faint shadow, a slight dimming. But at higher frequencies, the same cluster appears as a bright spot. This signature is unique, and its brilliance is its independence from distance. The apparent size of the shadow on the sky does not change with how far away the cluster is, unlike its optical light, which fades dramatically. This makes the SZ effect a phenomenal tool for conducting blind surveys of the universe, finding clusters based solely on their mass and hot gas content. Major projects like the Planck satellite and the South Pole telescope have scanned the entire sky, using this precise effect to catalog many thousands of previously unknown galaxy clusters, building a massive census of the largest structures in the cosmos. A stunning example of its power is the Bullet cluster, a system formed from a violent collision of two galaxy clusters. Observations showed that the dark matter, traced by gravitational lensing, had passed right through the collision, while the hot gas, revealed by its brilliant SZ effect signature and X-ray emission, was slowed and dragged behind, caught in a cosmic traffic jam. This provided some of the most direct visual evidence for the existence of dark matter. How does the interaction of the oldest light with the hottest gas reveal the architecture of the cosmos? This subtle scattering pattern does more than just find clusters. It measures the immense pressure that holds them together, a pressure shaped by the relentless pull of gravity and the opposing push of dark energy that governs the expansion of the universe itself. The geometry of space itself is not a fixed stage, but a dynamic fabric that stretches with time. This cosmic stretching creates a powerful 17th pattern, the Alcock-Paczynski Test, a geometric probe that uses the large-scale structure of the universe to measure its own expansion history. The test relies on a fundamental principle. The expansion of space affects our measurements of distance differently depending on the direction we look. Distances across our line of sight, the transverse direction, are measured by an object's apparent size on the sky. But distances along our line of sight, the radial direction, are measured by redshift, the stretching of light caused by the universe's expansion. If we know the true shape of a large structure in the universe, any mismatch between its radial and transverse dimensions reveals the precise geometry and expansion history of the cosmos. A theoretical cosmologist might describe this as a direct geometric test of the cosmic distance redshift relation, a way to measure the influence of dark energy without relying on standard candles or other indirect methods. This test is applied to the grandest patterns we know, the cosmic web itself. Astronomers look for a specific distortion, an anisotropy, in the correlation function of galaxies. This statistical map shows how likely you are to find two galaxies at a given separation. In a universe with no dark energy, this map would appear statistically spherical on the largest scales. But if dark energy is accelerating the expansion, a subtle squashing or stretching appears, distorting this cosmic fingerprint. The data required for this are immense, coming from massive redshift surveys like the Extended Baryon Oscillation Spectroscopic Survey or the Dark Energy Spectroscopic Instrument. These projects collect precise spectra for millions of galaxies and quasars, building a three-dimensional map of the universe's structure with unprecedented detail. They also analyze the Lyman alpha forest, the intricate absorption patterns in the light of distant quasars caused by clouds of neutral hydrogen gas. This forest acts as a dense grid of lines along the line of sight, making it exquisitely sensitive to radial distortions. Imagine a perfectly spherical cluster of galaxies at a great distance. If our cosmological model is wrong, and we misunderstand how space has stretched over time, this sphere would not appear round to us. Depending on the model, it might look squashed along our line of sight, or conversely, stretched out like a football. The Alcock-Paczynski Test is the tool that measures this distortion, using the universe's own large-scale structure as a calibrated ruler. What distortions in the cosmic map can unveil the true nature of dark energy? This geometric test, written in the relative positions of millions of galaxies, offers a direct path to answering one of cosmology's deepest questions. The subtle warping of space by mass offers another way to chart this invisible architecture. A funhouse mirror warps your reflection in a predictable way, revealing the shape of the curved glass. The universe has its own version of this effect, and it is the 18th hidden pattern: weak gravitational lensing and cosmic shear. Here, the mirrors are vast concentrations of dark matter, and the reflections are the distorted shapes of billions of distant galaxies. This is not the dramatic lensing that creates brilliant Einstein rings, but a far more subtle and statistical phenomenon. The gravity of all the matter along the line of sight, most of it invisible dark matter, ever so slightly bends the path of light from galaxies in the distant background. This causes a coherent, tiny distortion in their shapes, typically stretching them by less than 1%. A lead scientist from the Dark Energy Survey has described this painstaking work as weighing the universe with light, using the faintest of signals to measure the invisible. The principle comes directly from Einstein's theory of general relativity, which tells us that mass curves the fabric of spacetime. Light, traveling through this curved space, follows the bends, its path subtly altered by every galaxy, every wisp of dark matter filament it passes. No single galaxy's distorted shape is conclusive evidence. The breakthrough comes from statistics, by meticulously measuring the shapes of millions upon millions of galaxies and averaging the results. The random orientations of their intrinsic shapes should cancel out, leaving behind only the coherent pattern of distortion imprinted by the cosmic web of dark matter. This statistical map of distortion is what astronomers call cosmic shear. The challenges in this measurement are immense. Scientists must first understand and correct for the natural, oval shapes of many galaxies. Then they must account for the blurring effects of Earth's own atmosphere, which can mimic a lensing signal. Advanced image analysis and powerful supercomputers are required to clean the data and reveal the true, subtle warp. The Dark Energy Survey relies heavily on this technique. By measuring how the cosmic shear signal changes across different cosmic epochs, it probes how the growth of these large-scale structures has been suppressed over time by the repulsive force of dark energy. How can the slight warping of starlight reveal the invisible skeleton of the cosmos? It transforms every distant galaxy into a tiny marker, its distorted form tracing the gravitational signature of everything between it and us. This gentle bending of light, when applied to the most extreme objects in the universe, can reveal monsters hiding in plain sight. A perfect circle of light hangs in the void, a golden ring forged by gravity itself. This is the 19th pattern, the phenomenon of strong gravitational lensing and its most beautiful manifestation, the Einstein ring. It occurs when a distant galaxy, a brilliant quasar, and our line of sight align in a nearly perfect straight line with a massive foreground object, like a giant elliptical galaxy. The immense gravity of this cosmic lens warps the fabric of spacetime around it, bending the light from the faraway source and smearing it into a luminous arc, or, in the rarest of alignments, a complete circle. These are not mere celestial curiosities. As one expert in gravitational lensing has noted, they act as nature's ultimate telescopes, magnifying the light of galaxies so distant and faint that they would otherwise be completely invisible to our instruments. The geometry of this cosmic mirage is defined by the Einstein radius, a characteristic angle that determines the size of the ring. This radius depends directly on two key factors: the total mass of the foreground lens, including all its dark matter, and the relative distances between the observer, the lens, and the distant background source. A more massive lens or a more fortuitous alignment of distances will produce a larger, more pronounced ring. The lenses themselves come in many forms. A single massive galaxy can create multiple distorted images of a single background quasar, like a cosmic funhouse mirror. An entire cluster of galaxies, with its immense collective gravity, can sculpt fantastic arcs and smear distant galaxies into long, thin streaks of light. One of the most stunning examples is the Horseshoe Einstein ring, a nearly complete circle of blue light surrounding a distant yellow galaxy. The background galaxy is a vigorous star-forming system, its light bent around the foreground galaxy into this breathtaking shape. These lenses also introduce a fascinating temporal effect called time delays. Because the light forming each multiple image travels along a slightly different path around the lens, each image arrives at Earth at a slightly different time. By monitoring variations in the brightness of a lensed quasar, astronomers can measure this delay, which provides an independent way to calculate the expansion rate of the universe, the Hubble constant. What can these cosmic mirages teach us about the distribution of matter on all scales? They provide a direct and precise map of the total mass of the lensing object, revealing how dark matter is distributed within galaxies and clusters with unparalleled accuracy. The most extreme lenses of all are found around black holes. A dark circle, silhouetted against a brilliant ring of fire, became an icon of human curiosity. The first ever image of a black hole, captured by the Event Horizon Telescope collaboration, revealed the shadow of the supermassive giant at the heart of Galaxy M87. This was not a picture of the black hole itself, for no light can escape from within. Instead, it was a portrait of its gravitational influence, a dark void encircled by a luminous ring of photons, a pattern precisely forecast by Einstein's theory of general relativity. As one lead scientist from the EHT project expressed, this image was humanity's first direct glimpse into the environment of a black hole, a test of our theories in the most extreme gravitational regime imaginable. That central shadow is the point of no return for light. It is created by photons that venture too close to the black hole's event horizon, their paths so warped by gravity that they are either captured forever or bent into orbits that form a brilliant ring around the darkness. This ring marks the photon sphere, a region where gravity is so intense that light itself is forced to travel in circles. The brightness of this ring is not uniform. It appears as a brilliant crescent on one side, a consequence of the frenzied motion of the superheated gas in the accretion disk swirling around the black hole. The side of the disk spinning toward us appears dramatically brighter, its light boosted by a phenomenon called Doppler beaming, while the side spinning away appears fainter. This asymmetry is a treasure trove of information, revealing the black hole's direction of spin and the orientation of its voracious disk. To capture an image of something so small and distant required a telescope as large as the Earth itself. The Event Horizon Telescope achieved this by synchronizing a global network of radio observatories, from the high deserts of Chile to the volcanic peaks of Hawaii. By combining their signals, they created a virtual dish with a resolution sharp enough to read a newspaper in New York from a sidewalk cafe in Paris. The target, the M87 black hole, is a behemoth weighing 6.5 billion times more than our Sun. The size of its shadow, measured against the predictions of general relativity, perfectly confirmed the mass that astronomers had estimated through other methods. How does observing the absence of light confirm our deepest theories of gravity? It provides a direct silhouette of spacetime itself, warped beyond recognition, proving that even in the realm of the most monstrous objects, a profound order governs the chaos. This silent shadow is not the only signal these cosmic giants emit. The whirl of matter around a black hole is a cosmic drain, a final, furious dance before the plunge into oblivion. As superheated gas spirals inward at near light speed, it glows with an intense, fluctuating brilliance, especially in the high-energy realm of X-rays. Hidden within this flickering chaos is the 21st pattern, a rhythmic signal known as quasi-periodic oscillations. These QPOs are not the steady tick of a clock, but a quasi-regular pattern of rising and falling brightness, a signature of matter churning under the most extreme gravity in the universe. A high-energy astrophysicist might describe these oscillations as the heartbeat of the accretion flow, a natural probe of physics in a regime so violent it can never be recreated in any laboratory on Earth. The key to unlocking their message lies in their characteristic frequencies. Just as the pitch of a musical note tells you about the string that produced it, the frequencies of these X-ray oscillations encode vital information about the innermost stable orbits around the black hole or neutron star, a region where spacetime itself is dragged around by the colossal spin of the central object. One leading model that explains this cosmic rhythm is the relativistic precession model. It connects the observed frequencies to three fundamental clocks in the strong gravity region. The first is the simple orbital period, how long it takes a blob of gas to complete one full circle. The second is the periastron precession period, which is the slow rotation of the orbit's orientation, much like how Mercury's orbit slowly shifts around the Sun. The third is the nodal precession period, a wobble in the orbit's tilt caused by the dragging of spacetime. The interplay of these three effects creates the complex, quasi-periodic signal we observe. Astronomers categorize these flickers into two main families. Low-frequency QPOs are thought to originate from farther out in the accretion disk, where the gravitational grip is a bit weaker, and dynamical timescales are longer. High-frequency QPOs, in contrast, are believed to come from the very brink of the event horizon, where orbits are frantic and spacetime is stretched to its limit. A spectacular example of this wild variability is the black hole binary system GRS 1915+105. This system is a cosmic powerhouse, its X-ray output flaring and dipping in dramatic, almost predictable patterns that have been studied for decades, offering a rich dataset for testing these models of extreme gravity. What secrets about spacetime near a black hole are whispered in these flickering X-rays? They may hold the key to directly measuring a black hole's spin and definitively testing whether the predictions of general relativity hold true at the very edge of reality. Mercury's dance with the Sun is a masterclass in celestial precision. The small, cratered world spins on its axis exactly 3 times for every 2 trips it makes around our star. This is not a random cadence, but a profound gravitational lock known as a spin-orbit resonance. The Sun's immense gravity, working on Mercury's slightly oblong shape and its stretched, elliptical orbit, has gently coerced the planet into this stable, repeating rhythm over billions of years. A planetary scientist might describe this 3-to-2 resonance as the solar system's most elegant compromise, a state that minimizes the energy lost to internal friction and tidal heating. The physics hinges on a gentle but persistent tug of war. The Sun's gravitational pull exerts a torque on Mercury, especially when the planet is at the closest point in its orbit. This repeated nudge, acting on a world that is not a perfect sphere, has gradually braked and then reset its rotation until it settled into this perfectly synchronized spin. This is the same process of tidal locking that has given us a moon with a permanent far side, always hidden from Earth. Our moon is in a 1-to-1 spin-orbit resonance, completing 1 rotation for every single orbit. We see an even more intimate version of this with Pluto and its largest moon, Charon. They are mutually tidally locked, forever facing one another as they pirouette through the frozen depths of the Kuiper belt. This resonance creates a truly bizarre day on Mercury. If you could stand on its scorching surface, you would witness a sun that appears to move backward in the sky at times. A single solar day, from one sunrise to the next, lasts for 176 Earth days, which is precisely 2 Mercury years. How do these gravitational dances create stable niches in a dynamic solar system? They prove that even the most chaotic-looking orbital environments can settle into predictable, energy-efficient patterns over time. These resonant rhythms are not confined to planets and their moons. They also govern the orbits of countless small bodies within the asteroid belt. The asteroid belt between Mars and Jupiter is not the cluttered junkyard of popular imagination, but a region sculpted by gravity into zones of emptiness and congregation. These pronounced empty bands are known as the Kirkwood gaps, and they are a direct testament to Jupiter's distant but unrelenting influence. Within these specific regions, the orbital period of an asteroid would be a simple fraction of Jupiter's own, creating a perfect gravitational rhythm that spells chaos. An orbital dynamicist would call this celestial mechanics in action, where consistent, periodic tugs from the giant planet accumulate over millennia, destabilizing any asteroid unfortunate enough to be caught in the resonance. The key lies in the mathematics of the orbit. If an asteroid circles the Sun exactly twice for every one of Jupiter's orbits, it is in a 1-to-2 resonance. Every time the asteroid returns to that same point in its path, Jupiter is waiting, giving it an identical gravitational nudge. These repeated, clockwork perturbations do not cancel out. They add up, pulling the asteroid into an increasingly elongated and unstable orbit, until it is eventually ejected from the resonance zone entirely or flung toward the inner solar system. This process is a powerful demonstration of chaotic dynamics, governed by a concept known as the Lyapunov time. This is the timescale over which tiny, almost imperceptible differences in an asteroid's initial position or velocity are amplified exponentially by the resonance. Two nearly identical asteroids entering a Kirkwood gap could end up on wildly divergent paths, one ejected to the outer solar system and the other sent on a collision course with Mars, all because of a difference in starting conditions no greater than the width of a human hair. The most prominent gaps correspond to these simple, destabilizing fractions. The 1-to-2 resonance is a vast emptiness, while the 1-to-3 and 2-to-3 resonances create other significant voids. Bordering these gaps, however, you find the opposite phenomenon, stable asteroid families where groups of rocks share very similar orbits, likely the fragments of ancient collisions that occurred in the safe gravitational harbors between the resonances. Picture a single asteroid drifting for eons in a stable path. A chance encounter with a smaller rock gently alters its trajectory, just enough to nudge it into the precise rhythm of the 1-to-2 resonance with Jupiter. For thousands of years, its orbit seems only slightly more eccentric, but with each conjunction with the giant planet, the gravitational kick it receives is reinforced. Its path stretches further, becoming an oval that begins to cross the orbits of other asteroids. Finally, after millions of years of this relentless tuning fork effect, a final, decisive encounter with Jupiter's gravity flings it out of the belt entirely, sending it on a lonely journey through the solar system. How does the gravity of a giant planet sculpt the architecture of an entire belt of minor planets? It acts as a master clock, its rhythmic pull clearing out specific orbits and herding the remaining debris into stable families, imposing a clear and lasting order on what would otherwise be a true chaos of rocks. This same celestial choreography extends far beyond the asteroid belt, governing the distant, icy bodies of the Kuiper belt. Beyond the orbit of Neptune lies a frozen frontier, a vast disk of icy worlds known as the Kuiper belt. Far from being a random scattering of debris, this region exhibits a stunningly structured arrangement. a testament to the hidden order imposed by gravity. The 24th pattern is the architecture of the Kuiper belt itself, defined by its resonant populations and a mysterious concentration of objects called the Kuiper belt kernel. This kernel is a tightly packed group of bodies with nearly identical circular orbits, a puzzle that hints at a dramatic past. Even more striking are the mean motion resonances with Neptune. Pluto is the most famous resident of this ordered realm, locked in a stable 2 to 3 resonance with the giant planet. For every 2 orbits Neptune completes, Pluto makes exactly 3, a gravitational synchrony that keeps their paths from ever crossing. This resonance acts as a protective shield. The consistent rhythmic tugs from Neptune actually prevent close encounters, ensuring that objects like Pluto are never ejected from the solar system. A planetary astronomer might describe the Kuiper belt not as a chaotic leftover, but as a fossilized dynamical record, its structure preserving the story of the solar system's formative era. This fossilized record was carved by a grand migration. Early in the solar system's history, Neptune formed much closer to the Sun and then slowly drifted outward. As the planet moved, its gravitational influence swept through the primordial disk of icy bodies. Many of these objects were captured into stable resonances during this migration, like marbles being gathered by a moving sieve. The different resonant populations tell this story. Plutinos, like Pluto, all share that 2 to 3 resonance with Neptune. Another group, the Teutinos, are locked in a 1 to 2 resonance. Beyond these resonant families lie the classical Kuiper belt objects, which are further divided. The cold classical population consists of objects on relatively circular, stable orbits, likely the true primordial locals of the region. The hot classical population, with their more tilted and eccentric orbits, were probably scattered inward from other parts of the solar system before finding their current home. Pluto and its resonant family are a perfect illustration of this cosmic harmony. They are not alone, but part of a vast swarm of objects all dancing to the same gravitational rhythm. Their orbits synchronized with Neptune's in a ballet that has lasted billions of years. What does the structured emptiness of the outer solar system reveal about its violent youth? It shows a history of planetary wanderings and gravitational sculpting, a process that continues to shape the influx of comets from the even more distant Oort cloud. Our solar system's dominion stretches far beyond the planets, ending in a vast, silent reservoir of ice. This is the Oort cloud, a spherical shell of frozen planetesimals reaching nearly a light-year into the void. While the arrival of a brilliant long-period comet seems a random celestial event, its journey is guided by a subtle, statistical pattern. The gentle, rhythmic tug of the Milky Way's gravity, along with the occasional close pass of a wandering star, acts like a cosmic shepherd, perturbing these dormant icebergs and sending a steady trickle sunward. A solar system dynamicist might describe the Oort cloud as a sleeping reservoir of primordial material. Its slow leakage into the inner solar system, a direct window into the conditions of our planetary birth. The mechanism is a gravitational random walk. As our Sun orbits the galactic center, it passes through regions of varying density and feels the tidal forces of the entire Milky Way. Nearby stars, on their own independent paths, occasionally wander close enough to give the cloud a gravitational nudge. These combined influences do not produce a regular clockwork, but over millions of years, they generate a statistically predictable rate of cometary arrivals, a hidden order within the apparent randomness of cosmic fireworks. This spherical cloud is distinct from the flatter, more predictable scattered disk, which is the source of short-period comets like Halley's. The Oort cloud gives us the grand, unpredictable visitors. A perfect example is Comet Hale-Bopp, whose spectacular appearance in the 1990s was a once-in-millennia event. It arrived from the depths of the Oort cloud on an orbit that takes thousands of years to complete, a pristine messenger from the solar system's farthest frontier. Is the occasional bright comet a message from the very edge of the Sun's gravitational dominion? These icy travelers remind us that our solar system is not an island, but an integrated part of the dynamic galactic environment, its history and future written in the slow dance of gravity across incomprehensible distances. A galaxy's graceful spiral arms should not exist. Each star orbits the center at its own speed, with inner stars racing ahead while outer stars lag behind. This differential rotation ought to wind those majestic arms into a hopelessly tangled blur within a few galactic rotations. The fact that we see them at all, enduring for billions of years, points to a pattern that is not a physical structure but a moving ripple. This is the 26th pattern, the density wave theory of spiral arms. The spiral arms we admire are not permanent streams of the same stars. They are cosmic traffic jams, waves of compressed density that travel through the galactic disk like a sound wave moving through air. Stars and vast clouds of gas flow into this gravitational bottleneck, pile up temporarily, and then flow out the other side, all while the wave itself maintains its distinct shape. As one galactic astronomer famously noted, this elegant idea resolved the winding dilemma by revealing the arms as a pattern of motion, not a pattern of matter. The mechanics are a beautiful feedback loop. The wave's slight gravitational pull hurls stars and gas toward it, which increases the local density, which in turn strengthens the wave's gravity, making it self-sustaining. The most spectacular effect happens to the gas. As a giant molecular cloud enters the density wave, it is violently squeezed. This compression triggers the collapse of dense cores within the cloud, igniting the birth of brilliant, short-lived blue stars. These hot, young stars light up the arm, marking the wave's position with their intense radiation, before they explode as supernova long before they ever leave the spiral pattern. We see direct evidence for this sequence in some galaxies, where astronomers locate the shock front of the density wave itself, often traced by dust lanes, just ahead of the brightest blue star clusters. Our own Milky Way is a grand example. Its spiral structure is not defined by a single static wave, but is likely driven and shaped by the gravitational influence of its central bar and periodic gravitational nudges from satellite galaxies like the Large and Small Magellanic Clouds. How can a pattern that is not made of permanent matter shape the evolution of an entire galaxy? By orchestrating the rhythm of stellar birth and death, these density waves turn chaos into a sustained, rotating symphony of creation. This grand spiral structure is not only shaped by gravity, but also by a far more subtle force woven through the interstellar void. An invisible force threads through the void between the stars, a cosmic magnetism that guides and structures the galaxy. These large-scale galactic magnetic fields are the 27th hidden pattern, an ordered architecture often perfectly aligned with the majestic spiral arms. We cannot see these fields with our eyes, but we detect them through the polarization of radio waves, a specific type of emission called synchrotron radiation that is generated when high-energy electrons spiral around magnetic field lines at nearly the speed of light. As one radio astronomer has expressed, measuring these fields is like seeing the galaxy in a new light, revealing an entire dimension of its structure that was previously hidden in darkness. These magnetic fields are far from passive decorations. They act as a galaxy-wide containment system for cosmic rays, the ultra-high-energy particles that race through space. The fields trap and channel these rays, preventing them from escaping too quickly and shaping their journey across the galaxy. They also play a crucial role in the delicate balance of star formation, providing pressure support to vast molecular clouds that can either resist or encourage their collapse into new suns. The origin of these immense, organized fields is a process that unfolds over billions of years, described by the galactic dynamo theory. This theory posits that the combined energy of the galaxy's rotation and the turbulent motions of its ionized gas can amplify a tiny, primordial seed magnetic field, stretching and twisting it into the coherent, large-scale structure we observe today. It is a self-sustaining cycle, where motions in the conductive gas generate electrical currents, which in turn reinforce the magnetic field. To map this invisible scaffold, astronomers use a phenomenon called Faraday rotation. When polarized light from a distant quasar or radio galaxy passes through the Milky Way's magnetized interstellar medium, the plane of its polarization is subtly rotated. The amount of this rotation tells scientists the strength and direction of the magnetic field along that specific line of sight. By observing thousands of these background sources, they can painstakingly reconstruct a three-dimensional picture of our galaxy's magnetic personality. Our own Milky Way possesses a complex magnetic character. In its spiral arms, the field exhibits a surprisingly coherent direction, running parallel to the arms themselves, as if tracing the path of the density wave. Elsewhere, in the spaces between the arms and in the galactic halo, the field becomes more chaotic and disordered, a turbulent froth of magnetic energy. What role does this cosmic magnetism play in the ecosystem of a galaxy? It is the silent partner to gravity, a fundamental force that weaves through the interstellar medium, influencing everything from the journey of a single cosmic ray to the grand cycle of stellar birth and death. Deep within a cold, dark molecular cloud, a single dense core begins to collapse under its own weight, destined to become a star. But this is not a simple, headlong fall. An invisible architecture of magnetic field lines permeates the gas, acting as a powerful brake against gravity's relentless pull. These fields provide crucial support, regulating the entire collapse and directing the flow of material with a hidden hand. As one star formation theorist described it, magnetism is the quiet choreographer of stellar birth, preventing a rapid, chaotic collapse and ensuring a more orderly, prolonged construction process. The pattern of these magnetic fields, often revealed by the subtle polarization of light emitted by interstellar dust grains, serves as a cosmic funnel. It channels material from the vast surrounding envelope down onto the forming protostar and its nascent planetary disk, guiding the very stuff of worlds into place. This process, however, presents a profound puzzle known as the magnetic flux problem. If all the magnetic field lines from a gigantic, diffuse cloud were dragged inward and perfectly conserved during the collapse, the resulting star would possess a magnetic field trillions of times stronger than anything observed. Such an intense field would halt the collapse entirely, preventing stars from ever forming. Nature resolves this contradiction through a subtle, slow process called ambipolar diffusion. In this mechanism, neutral atoms and molecules which feel only gravity gradually drift or diffuse through the ionized gas that is frozen to the magnetic field lines. This allows the neutral material to decouple from the magnetic field and slip inward to fuel the growing star, while the magnetic flux is left behind in the outer regions. Modern radio telescopes like the Atacama Large Millimeter Array, or ALMA, have given us stunning visual proof of this hidden order. In numerous protostellar cores, ALMA-sensitive polarimetry has revealed beautiful, hourglass-shaped magnetic fields. The field lines are pinched at the center where the protostar is forming and fan out symmetrically above and below, a perfect match to the theoretical predictions of how a magnetically regulated collapse should appear. A prime example is the Orion Molecular Cloud, a vast and nearby stellar nursery. Here, astronomers are meticulously mapping the magnetic fields threading through the glowing gas, correlating their structure with the positions of newborn stars and protoplanetary disks. They are finding that the strength and geometry of these fields directly influence how efficiently gas can collapse, and even how many stars of different sizes a cloud will produce. How does the invisible architecture of magnetic fields determine the mass and number of stars born? It is this delicate balance between the inward pull of gravity and the outward pressure of magnetism that sets the final blueprint for a solar system, governing the very first steps in the journey from a cloud of gas to a family of planets. A simple sequence of numbers once seemed to map our solar system. The Titius-Bode law, proposed in the 1700s, is a curious numerical pattern that predicted the average distances of the planets from the Sun with uncanny accuracy for its time. The rule starts with 0, then 3, and then doubles each subsequent number. So the sequence is 0, 3, 6, 12, 24, 48, and 96. You then add 4 to each number and divide by 10 to get the distance in astronomical units, the average Earth-Sun distance. This simple formula placed Venus at 0.7 astronomical units, Earth at 1.0, Mars at 1.6, and Jupiter at 5.2, all strikingly close to their actual orbits. Most famously, it predicted a gap at 2.8 astronomical units, a void between Mars and Jupiter where no known planet resided. This apparent pattern fueled a determined search, leading Giuseppe Piazzi to discover the dwarf planet series in exactly that region in 1801, a finding that later revealed the vast asteroid belt. A modern planetary dynamicist might describe the law not as a fundamental force of nature, but as a fossilized echo of the protoplanetary disk structure. It hints at the underlying processes of planetary accretion, where gravitational interactions and orbital resonances tend to space forming planets apart in a non-random, quasi-regular manner. The pattern works reasonably well for the inner solar system because the planetary formation process there was likely more orderly, with less dramatic migration. Its most spectacular failure, however, is with Neptune. The law predicts a planet at 38.8 astronomical units, but Neptune resides at just 30.1, a significant deviation that revealed the pattern's limitations. The law is now understood not as a cause, but as a likely consequence of dynamical evolution. In the early solar system, protoplanets may have migrated, clearing their orbits and settling into stable configurations spaced apart by mutual gravitational interactions, sometimes falling into resonant arrangements that produce these approximate geometric progressions. Today, the search for similar spacing patterns is a key part of exoplanet research. Astronomers analyzing systems like TRAPPIST-1, with its 7 rocky worlds, look for signs of such resonant chains and non-random architecture, seeking to understand if our solar system's rough spacing is a common outcome or a cosmic fluke. Was this centuries-old numerical coincidence a genuine glimpse of a deeper ordering principle in how planetary systems are built? The answer may lie in the statistical patterns now being uncovered in thousands of worlds around other stars. The Kepler Space Telescope's census of thousands of distant worlds revealed a startling void in the cosmic catalog. Amidst a sea of data points, a clear desert emerged, a scarcity of planets with sizes between 1.5 and 2 times Earth's radius. This is the radius gap, a pattern so pronounced it divides the population of small exoplanets into 2 distinct families. On one side, you have the rocky super-Earths, dense worlds like our own but larger. On the other, the puffy mini-Neptunes, planets with thick, gaseous envelopes hiding a smaller core. The gap between them is not a quirk of detection, it is a forensic clue written across the galaxy. One exoplanet scientist described it as the signature of a great planetary evaporation, a process that systematically strips away the atmospheres of certain worlds, leaving their fate sealed by their initial size and orbit. The primary culprit is the ferocious radiation from a young star. In a process called photo-evaporation, intense ultraviolet and X-ray radiation can boil away the primordial hydrogen and helium envelope of a planet that orbits too closely. The star's heat provides the energy to drive the atmosphere off into space, a relentless stellar wind that scours worlds clean. There is another mechanism, too, known as core-powered mass loss. Here, the latent heat from the planet's own formation, still simmering in its rocky core, provides the energy to slowly push the atmosphere away over billions of years. Whether the blowtorch comes from the star or the planet's own heart, the result is the same. A world that starts as a mini Neptune, if it has just a little too little mass to hold on, can have its entire gaseous shell peeled back, leaving behind a naked, rocky super-Earth. The location of this radius gap in the size orbital period diagram is not random. It shifts predictably based on the type of star. Around quieter, smaller M-dwarf stars, the gap appears at a smaller planetary radius than it does around more Sun-like stars, because the same destructive processes operate at different intensities. This creates a visible diagonal line across the chart of known exoplanets, a stark boundary between two evolutionary destinies. Consider our own solar system as a miniature version of this cosmic divide. We have the rocky inner planets like Earth and the gaseous giants of the outer system like Neptune. What we lack are any true in-between worlds, planets with sizes squarely in the Fulton Gap, because our local conditions favored one path or the other from the very beginning. What does this great evaporation, this desert in the planetary size distribution, tell us about the fate of worlds? It reveals that a planet's character is not fixed at birth, but is forged by its lifelong relationship with its star, a relationship ultimately written in the planet's final density. Two simple numbers can reveal the entire history of a distant world. Given a planet's mass and its radius, what is it truly made of? This is the fundamental question answered by the 31st pattern, the mass-radius relationship for exoplanets. It is a cosmic diagnostic tool, a plot that allows astronomers to look at a dot representing a far-off world and infer whether it is a barren ball of rock, a global water world shrouded in a deep ocean, or a puffy gas dwarf with no solid surface at all. The rule is elegantly direct. For a given planetary mass, a larger radius signals a significant, lightweight envelope of gases or ices, while a smaller, more compact radius points toward a dense composition dominated by iron and rock. A leading planetary scientist has called this relationship the Rosetta Stone for interpreting exoplanet data, the key that translates basic measurements into a story of planetary character and formation. This key is forged from complex models of planetary interiors. Scientists use equations of state, which describe how materials like iron, silicate rock, water ice, and hydrogen gas behave under the crushing pressures inside a planet, to generate theoretical curves. There is a curve for a pure iron world, another for a purely rocky planet, another for a water world, and another for a gaseous body made mostly of hydrogen. When you measure a real exoplanet, you place it on this diagram to see which curve it falls closest to, revealing its most likely bulk composition. Yet this powerful tool comes with a crucial caveat, the problem of degeneracy. Different internal mixtures can sometimes produce the same mass and radius. A planet with a large iron core and a thick, light mantle might look identical, from this data alone, to a world with a smaller core and an enormous global ocean. This ambiguity forces scientists to be detectives, combining the mass-radius data with other clues, like the planet's orbital distance and the properties of its star, to build a consistent portrait. We can see this detective work in action with the famous TRAPPIST-1 system. The 7 Earth-sized planets have had both their masses and radii measured with remarkable precision. When plotted on the mass-radius diagram, most of them cluster close to the curve for rocky compositions, much like Earth and Venus. This strongly suggests they are terrestrial worlds. However, some of the outer planets appear slightly less dense, hinting that they could possess significant reservoirs of water ice or perhaps thick, steamy atmospheres. making them potential water worlds rather than arid rocks. This directly impacts the search for habitability. A planet that plots directly on the rocky Earth-like curve is a prime candidate, while one that falls on the water world line might be a globe-girding, pressurized ocean, a fascinating place, but perhaps not one we would recognize as home. How can two simple measurements unlock the secret composition of a distant world? They provide the first, crucial glimpse past a planet's reflected starlight, down into its very heart, separating the rocky candidates from the gaseous mirages. This intrinsic character of a planet is profoundly shaped by the star it calls home. Our own sun pulses with a quiet rhythm, an 11-year heartbeat of magnetic activity. This familiar cycle, marked by the ebb and flow of sunspots, is far more than a solar curiosity. It is the engine of space weather, generating solar flares and coronal mass ejections that can disrupt satellites and power grids on Earth. And our star is not unique. Across the galaxy, other sun-like stars exhibit their own activity cycles, with periods ranging from a few years to several decades, a hidden metronome ticking within their fiery hearts. These stellar rhythms are governed by internal magnetic dynamos, colossal engines of circulating plasma that generate and twist magnetic fields. The resulting cycles dictate the strength of the stellar wind, the frequency of violent flares, and the intensity of ultraviolet and X-ray radiation that bathes any orbiting planets. A heliophysicist might state that to assess the true, long-term habitability of an exoplanet, we must first understand the temperament of its sun, the character of its space weather as defined by these magnetic cycles. The most successful model for our own sun's cycle is the Babcock-Leeton model. It begins with the sun's differential rotation, where the equator spins faster than the poles. This shear stretches and winds up the global magnetic field, wrapping it around the star like a tangled ball of string. Over time, these wound-up magnetic fields become buoyant, kinking and rising through the solar plasma to burst through the surface as sunspot pairs. The final, crucial step is the decay and dispersal of these sunspots. As they break apart, their magnetic fields are carried by solar winds toward the poles, a slow circulation that eventually tears down and reverses the sun's global magnetic polarity, resetting the entire 11-year cycle. We detect these magnetic heartbeats in other stars through long-term monitoring projects, like the Mount Wilson HK project. Astronomers measure subtle changes in the light emitted by calcium in a star's chromosphere, its outer atmosphere. When magnetic activity is high, these specific emission lines brighten, creating a clear, periodic signal of the star's hidden dynamo at work. The consequences for a planetary system can be profound. Imagine a world orbiting a star with a much stronger and more violent cycle than our sun's. During a period of peak activity, a barrage of powerful flares and an intensified stellar wind could relentlessly batter the planet. For a close-in, rocky world, this sustained assault could slowly but surely strip away its atmosphere, evaporating any oceans and scouring its surface bare, transforming a potential paradise into a barren rock. How does the heartbeat of a star dictate the climate and fate of its planetary children? This stellar variability, a fundamental pattern of magnetic life, extends all the way to a star's final, dramatic death. A star's violent death becomes a cosmic measuring tape. Type Ia supernova are among the most crucial tools in all of cosmology, prized for their remarkable consistency as standardizable candles. Their true power lies not just in their immense brightness, which can outshine entire galaxies, but in the precise pattern of their light curves. Each of these stellar explosions follows a predictable script, a graph of brightness versus time that rises sharply to a brilliant peak and then steadily fades away. While no two are perfectly identical, they reveal a hidden order through the Phillips relationship. This key correlation shows that the rate at which the supernova's light declines after the peak is directly linked to its intrinsic luminosity at that peak. A supernova that fades more slowly was inherently brighter from the start. This single pattern allows astronomers to calibrate each explosion, to look at how quickly it dims and thereby know its true cosmic scale wattage. A supernova cosmologist might reflect that this Phillips relationship was the precise key that unlocked the door to the accelerating universe, turning a brilliant flash into a precise distance measurement. The physics behind this reliable uniformity is rooted in a catastrophic trigger. These events are thought to be the thermonuclear detonations of white dwarf stars. A white dwarf is the dense, Earth-sized core of a Sun-like star, supported against gravity by a quantum mechanical pressure. It can exist in a stable state until it accretes enough material from a companion to reach the Chandrasekhar mass limit, a critical threshold of about 1.4 times the mass of our Sun. At this precise point, the internal pressure can no longer hold back the crush of gravity, and the entire star is obliterated in a runaway fusion reaction. Because this explosion always ignites at nearly the same mass, the physics of the blast and the resulting light it produces are remarkably repeatable. Yet, a lively debate continues about the exact path to this cataclysm. The single degenerate scenario involves a white dwarf steadily siphoning material from a companion star like a red giant. The double degenerate scenario proposes the merger of two white dwarfs in a tight binary system, spiraling together until their combined mass exceeds the limit. Both pathways can lead to the same brilliant, standardized finale. When astronomers observe a Type Ia supernova in a distant galaxy, they immediately begin measuring its light curve. They take the observed data points of its brightening and fading and stretch or compress the universal template curve in time, and scale it in brightness until it fits perfectly. This fitting process, guided by the Phillips relationship, tells them the supernova's true peak luminosity. By comparing that known intrinsic brightness to its apparent dimness from Earth, they calculate the distance to its host galaxy with phenomenal accuracy. How does the predictable death of a white dwarf serve as a beacon across billions of light years? It is a cosmic bomb with a known yield, its flash illuminating the vast expanses of space and time. The explosions of massive stars follow a different path.